In this video, we are going to talk about equilibrium. We're going to talk about reactions that not only proceed in the forward direction, but can actually proceed in the reverse reaction, meaning the products can react with each other to reform the reactants. I want to talk about how we identify reactions at equilibrium, how we talk about the math involved in that, and then the factors that affect how those reactions sit at equilibrium. So at this point, we've spent a lot of time talking about reactions, right? We've talked a lot about reactants reacting with each other to form products. And we've pretty much walked away and left it at that. What we have not talked about is that reactions can proceed in both the forward, right? So if I have this reaction here, H2 plus I2 gives me 2HI. This particular reaction can also happen in the reverse, where 2HI react with each other to give me H2 and I2. Now, a reaction is considered at equilibrium when the rate of the forward reaction is equal to the rate of the reverse reaction. And when we have a reversible reaction like this, we generally write it in the forward direction, kind of the way I have the first one, but then we use a double arrow here, and that double arrow is going to indicate that the reaction proceeds in both the forward and the reverse direction. Okay, so the next thing we're going to talk about is the equilibrium expression. This is going to allow us to quantitatively talk about these reactions at equilibrium and to talk about whether there's more products when the system's at equilibrium or more reactants, or whether they're about equal. So to write out or we define a few things in this equilibrium expression first. So this is in general what our equilibrium expression is going to look like. KEQ is called the equilibrium constant. And this equilibrium expression is being written for this generic reaction that I have here. And so what you're going to see is that it is the products of the products raised to the power of the coefficient divided by the reactants raised to the power of their coefficients. We generally put them in terms of concentration, so it's the concentrations of the products divided by the concentration of the reactants, and then again it's raised to the power of that coefficient. And so those brackets are going to generally represent concentration, usually in terms of moles per liter. So I want to take you through a example, and we'll write out the equilibrium expression first, and then we'll plug in the values to figure out our equilibrium constant. All right, so KEQ is going to be equal to, now I've got my reaction right here, and my products are HI, and the coefficient is 2. So I'm going to put the concentration of HI in the numerator and square that since my coefficient is 2. And then I have H2 and I2 as my two reactants, and they both have a coefficient of 1. So I will have H2 times 8O times I2. Okay, so that is my equilibrium expression. I can now take my values and put them into that expression. So I have 0.50 squared over 0.25 times 0.25. Okay. So I'm going to go ahead and plug the numbers into the calculator, and when I do that, I get a value of 4.0, and I do want to make sure that I do include two significant figures. Since all of my concentration values have two significant figures, and I'm doing multiplication division. All right, so let's talk about what those numbers mean. So what does the magnitude of that equilibrium constant represent? Well, if K is less than 1, and in general we're talking smaller than 0.01, then the reactants are going to be favored. So think about the equilibrium leaning to the left side of the reaction. What this means is that the concentration of your reactants is greater than the concentration of your products. If K is larger than 1, and generally we're talking larger than 100, then this means that the products are favored, which means that that equilibrium lies towards the right side of the reaction. What this means is that the concentration of your products is greater than the concentration of the reactants. Now, K is equal to 1, and so we're going to define this as being between 0.01 and 100. Then both reactants and products are in equal amounts. So when you look at that value, you should be able to tell whether your reactants are favored, your products are favored, or whether they're about equal. And it's going to, again, depend on the magnitude of that number. Now, the last piece of information for you is that solid and liquid states are not included in the expression or the calculation. We are only going to include gases and solutions, so things that are aqueous, in the expression and the calculation. And the reason for this is that the concentration of solids and liquids stays relatively constant. And so they are generally going to stay the same at equilibrium. And so if they're not going to change, then there's no need to put them in the expression.